So here we are, we're being given a function right here. And so as you can see, it's a cubic function. It's being divided by 9, so just know that that does not change anything in terms of it becoming rational, because that's just a constant. There's no variables in that. So this is just a polynomial. Because it's of degree 3, it's this one, as you can see. And then its derivative, f prime, has already been found for us. We don't have to do it. And that is right here. That's the quadratic, as you can see. So now what I want you to do is take a few moments and estimate what the derivative is at these values. Now here's what I want you to understand. Because the derivative is the slope of the line tangent to the function at any point, what that means is that to find f prime of 1, all you need to do is look at the derivative function, f prime, and see what the y value is. So for example, here is our function f of 1. So here's our function f, and here's f of 1 right here. So as you can see on the original function, f of x, the tangent line at 1 is horizontal. And a horizontal line has slope 0. But notice that is also the y value of the derivative function. It's 0. So the answer to the first one is just 0. Okay. Now I'll quickly do the second one, and then I'm hoping that you guys can take a few moments or a moment or two and see if you can do the other ones. So f prime of 2, here's 2. So here's our original. So our job is to find the slope of the line tangent to that function. That's what it means to say f prime of 2. But because we have the derivative, and because the y value of the derivative at 2 is what we're looking for, because that's by definition of what a derivative is, it's a slope, we just need to estimate this value right here. So you can see it's about, I don't know, it's up to you, 1.3, 1.4. It's just, a guess. You can even do this if you want. And so go ahead and see if you can come up with the other values for the other 4, pause it, and then come back and see if you are right. Okay, so for f of 4, here is our original function. So here's another good example of that same idea. At 4, we have this horizontal line, and that horizontal line is telling us that, we have a slope of 0, and we look at our derivative, and our derivative's y value is 0. So there's that relationship. Now, if we look at 3, it's not quite as nice, we have to estimate here, but we're estimating the slope of this line tangent. I did the best I could, and notice that that is a positive slope on that line, so it's not surprising that our slope is positive. It's the y value right here on the derivative, which is maybe about 1.2 or so. Yeah. Again, just an estimate, maybe about 1.2. And then f prime of 0, so now we're going to come all the way over here to 0. So we got to make sure we have, okay. So here's the function. So notice that we're finding the tangent line on our original function. Notice that this tangent line doesn't look great, but it has a negative slope. So it's not surprising that the derivative is down here. As you can see, the derivative is down here. And, that's like a negative 2 point something, maybe 2.7, I'm going to estimate. If you were close, no problem. It's just an estimate. And then for 5, we see as well that at 5, I'm not even close to the tangent line. There we go. Kinda. We got our tangent line at 5. Again, that is a straight line, but it has a negative slope. So we're going to head down, and we're not surprised to see that we're down here. And that's a pretty steep slope on that. And so, again, not too surprised to see that, that's going to be really the same as what we just got because of the symmetry on either side. So we're looking at about that negative 2.7. Okay. So that's an example of, that idea of like graphically, how do those relate? Okay, so now our job is to take f of x being the absolute value of x, and finding the derivative of that. So you should take yourself back to what this function looks like. This is absolute value of x, so absolute value of 0 is 0, absolute value of 1 is 1, 2 is 2, 3 is 3, nothing exciting there. Try to do the best you can for that straight line. On the other side, however, when we think about some x values, if we put in -1, we get +1, -2, we get +2, -3, we get +3, and so on. And so down we are like this. Okay, so here's our absolute value function. So our job is to find the derivative. What I want you to notice is we just have some lines here, but of course we have the absolute value, so that adds another like layer. So f prime of x is just doing what we normally do here. Limit as h goes to 0 of x plus h minus the absolute value of x over h. Okay. Now, this is where it gets, I don't know if I want to say tricky, but, you know, we have to think about the fact that we have two very different things on either side of 0. I mean, we have two separate lines. And so that's, you know, where the trickiness comes in. So what we do is we separate this into its two pieces. And this is, you know, a higher level kind of derivative idea. But we're going to look at the two pieces. So I'm going to separate them out. I'm going to look at the line on the right side. I guess if you're opposite me is over here. Limit as h goes to 0. And that line there, this line here, I want you to notice is just y equals x. Whereas this line over here is y equals -x. Of course, they switch at x equals 0. So if we just think about the function y equals x, well, that's just x plus h minus x over h, because it's whatever value you put in, you get, you know, on the positive side, that's what comes out, and that's for x greater than 0. However, when you think about this other line, y equals -x, the idea here is because x is less than 0, your absolute value is the negative of that negative number. So we would have -x minus h minus a -x. So that's plus x. So it's the negative of x plus h and the negative of x. And that's for x less than 0. Now, you should probably see, hopefully, that x plus h minus x, the x's simplify, the h over h is just 1, so we get 1. But we're not surprised to see that because the derivative of, well, the derivative is the slope of the tangent line, but these are already lines. So the derivative is just the slope of it. And so you can see that the slope of the line on the right side is 1, and the slope of the line of the left side is 1. So when we find the derivative, it's not surprising to get 1 and -1. And so, I mean, it makes sense, again, because the derivative is the slope. So of course, the only issue is at x equals 0. So what would be the derivative at x equals 0? And that's where we really kind of have to think about it. Because if we think about just that value, I want you to think about the fact that the way that we can do it is instead of x, in our limit definition, we just use 0 because we're finding at a certain point. So absolute value of 0 plus h minus absolute value of 0 over h. And that's just the limit as h goes to 0 of the absolute value of h over h. Okay, but as you might be able to tell, when you look at that limit, when you look at one side of it, so the limit as h approaches 0 from the left-hand side, you're going to have -h over h, or -1. So as you look at h approaching 0 from the positive side, you have h over h, and that's just 1. So the idea here is the limit on each side of 0 doesn't agree. And because the limit on each side of 0 doesn't agree, we have a limit that does not exist, you know, on either side of 0. So when we think about finding the derivative of f prime of x, and I'm gonna have to write it up at the top just because things are getting a little tight there for me, as I'm sure you can understand, we would say that f of x, this function, does not have a derivative at x equals 0. It can't exist because the limit doesn't exist from either side. So this function has a derivative on every other location except at that x equals 0. And that brings up a larger point, which is that there are times when derivatives don't exist. And that is when the graph has a corner. So you got that sharp corner that we see there. You could also have a cusp. And a cusp looks more like this. It doesn't go over itself. It's just like a little, oh my gosh. So the cusp is, if you were to say graph x to the 2/3, you're going to see a cusp. And so a lot of those functions with rational exponents have this idea here of a cusp. We'll see it. And also, something that's probably makes a little more sense, pretty straightforward, is any place where there's a discontinuity, you wouldn't have a derivative. So, you know, if you had a function that was like this, you're not going to have a derivative where the whole is. If you were to have a function like this, you know, you're not going to have a function where the whole is. You're not going to have a function where that value is, right? Because there's that jump there. And you don't have limits agreeing from either side. In those cases, if you were to try to take the derivative, you're going to get something like plus or minus infinity. And that's obviously not a real number, so we have an issue finding the derivative in that case. If a derivative exists, the function is called differentiable at the point. So if it's different, if f prime of a exists, then the function is differentiable at a. The function can also be differentiable on an interval if the derivative exists at every value on the interval. So just like we saw, we are not differentiable for x, you know, f of x equaling the absolute value of x at x equals 0. However, it is differentiable all the way up until 0 and for everywhere after 0. So it's differentiable everywhere else. I've already mentioned that. Another thing that we can do, so these are some kind of notes and definitions here, is that besides taking the first derivative of a function, you can take the second derivative, you could take the third derivative, you could take the 100th derivative. We will not be doing that, but you could, for functions. And so the second derivative, typical notation is f double prime. That's the second derivative of f. We use some different notation for that, not too surprising. We've got this one. So notice the 2 there, that's the big point. Not surprisingly, we have y double prime, that's common. Depending on what you have, you might see it with the x. And then we have this here. So typically the first ones you see more, that last one you don't see that much. So let's remind ourselves from earlier in this section, we have a function and we found its derivative. So we did that. Its second derivative is just the derivative of the first derivative. So all we would have to do here is just go f double prime of x. That's it. And now we're just doing the limit as h goes to 0 of that 2x minus 3. So f of x plus h minus f of x over h. So if you want, you can pause, see if you can complete this, evaluate it, see what you get. What we're going to find, not surprisingly, is that our 2x's simplify, our 3's simplify, so many things are gone. We get the limit as h goes to 0 of 2h over h. So of course that simplifies. We get the limit as h goes to 0 of 2. And what we learned before is that when you have a constant that you're taking a limit of, the answer is, of course, just that constant. So we just get 2. And that's the idea of a second derivative. It's literally just exactly the same. It's just the next derivative from the first derivative, but it follows the same definition. All right, just a couple more notational things to think about. We've got the fact that the derivative is the slope of the tangent line. The derivative is also the rate of change. Second derivative is the rate of change of the rate of change. Exciting. But it comes in handy. When we think about the position function, we learned that the derivative of the position function is the velocity function. So then when we take the second derivative of the position function, which is the derivative of the velocity function, that gives us this, which you might recognize just seeing the A there. It's acceleration. So, you know, it's one thing to be going 60 miles per hour. It's another thing to have your foot on the gas and actually be increasing your speed. That's acceleration. So that's different than just how fast you're going. Now, I will not be talking about this much more in class at all. You will never hear me say it again. But as a note, you could take the third derivative of the position function, and that is actually called the jerk. But we're not going to see anything more than that. Like I said, you could take all sorts of derivatives. You could have y triple prime. Once you get into the fourth derivative, typically we just do something like this, which might be kind of confusing for people that are like, wait, am I raising it to a power? Fourth derivative is not super common anyway. But we do have, you know, notation that's very similar to all the notation that we're seeing. It's not super exciting. You can probably guess at this point because all this follows a pattern. So it's just talking about taking it when we're using this big D, we're talking about, you know, the differentiation that happens. Okay. What do I need to do here? 4. That's right. Okay. So what I want you to see is this is the function that we had earlier. We found the first derivative. It is 2x minus 3. We just found the second derivative. It was 2. And then the third derivative is just the derivative of 2. But remember, the function 2 is just a straight line, a horizontal straight line. So the slope of a horizontal straight line, well, not surprisingly, that is 0. So those are all the derivatives. That's as far as you can go. You can't, I mean, you could take the fourth derivative or the fifth or the sixth, everything's going to be 0 from now on. And that's very typical. That's what happens with polynomials, is that sooner or later, by taking more and more derivatives, you get down to the point where you have a constant, and then your last derivative becomes 0. Theorem. If f is differentiable at a, then f is continuous at a. So that's a really handy thing to know. If something is differentiable, then it is continuous. So if you think about that, notice that the converse is not true. So you could have something that is continuous, but that doesn't mean it is differentiable. So as we've already learned, we've already seen the absolute value situation. Ooh. But you've already seen this. So this is continuous, but we've already learned not differentiable at x equals 0. Okay, so continuity does not imply differentiability. I've already kind of talked about the cusp. Here's like a bigger graph of what a cusp would look like. So this is going to have an infinite limit at x equals 0, but it's definitely not going to be differentiable. You're not going to be able to find the limit there. One other example, I'm going to do the best I can. Let's see, do I want to come from the top? Okay. So you could have a function that does this like kind of that, you know, like an x to the 1/3, like an x to the 1/3. So if you graph that somewhere, you'll see what I'm talking about. But the idea here is there's this place at x equals 0 where the tangent line is a vertical line, and you can't find the slope of that. And so there's no differentiability at x equals 0. For all of these, every other place is differentiable, but there is one value on them that is not. So continuity does not imply differentiability. And that is section 2.2.